Good morning. So a little bit of housekeeping to do before we get going here. So for those of you who don't know me, my name's Craig Scott. I'm the Director of Preservation and Research here at the museum. On behalf of the Royal Tyrrell Museum Cooperating Society and the Royal Tyrrell Museum of Paleontology, I'd like to welcome everyone to the 2024 Royal Tyrrell Museum Cooperating Society Speaker Series. After what can be fairly characterized as, I think, a trying and strange last few years, I'm very happy to announce that nearly all of the talks slated for this year's speaker series will be in person. And I think this marks a welcome return to live presentations, and I think a return to a much more enriching atmosphere that isn't always easy to replicate in virtual sphere. We have an intriguing slate of talks this year, drawing on expertise from the RTMP as well as the national and international scientific communities. This year's talks span many disciplines within the earth and biological sciences and will be delivered by guests from Canada, the United States, and from places as far away as Romania and Australia. I am delighted to introduce our guest for this morning's inaugural 2024 Speaker Series talk. Dr. Donald Henderson is the Tyrrell Museum Curator of Dinosaurs. Donald holds a Bachelor of Science in Geophysics from the University of Toronto and a PhD in Vertebrate Paleontology from the University of Bristol in England. And despite officially being a dinosaur researcher, he also studies other fossil reptiles such as pterosaurs, mosasaurs, ichthyosaurs, and plesiosaurs. He is especially interested in how the strange and gigantic animals of the past functioned as living, breathing, moving organisms. To conduct this research, he regularly develops and studies both static and animated three-dimensional computer models of various dinosaurs and other extinct creatures. His geophysics background compels him to retain an interest in the planets, their compositions, and their physical properties. Donald's talk this morning, quasi-poetically titled Earth and Mars, One Wet, One Dry, Why?, will explore one of the key questions in understanding how life on Earth evolved. The talk will probe the origins of the solar system and where water came from, show how the different sizes and positions of Mars and Earth led to very different water fates, and demonstrate some of the key properties of water for the maintenance of life on Earth. And so with that, would you please join me in welcoming Dr. Donald Henderson to the podium.
So as Craig's mentioned, I want to talk about a topic that I find quite interesting, is the fates of two different planets that started very close together in the solar system, and yet they turned out to be very different in the end. And unusually for me, for my presentations, there's no equations in this talk, because normally I'm very mathematical. There is a chemical equation, but there's no math. But there's heaps of math behind what I'm presenting, but you're spared the sordid details. So, these two planets, here's how I want to approach this topic. Why is water important for life? It's really an amazing substance. And then you have to look at the bigger picture. How did the solar system form? Because these planets are part of the same solar system. And then how did the formation of the solar system determine where the water would be? Because that's another really important part of the story. And then given this basic background, large scale, you say, how did two different planets end up being so different? And then lastly, say, what are some of the important consequences for having a wet planet, especially in terms of history of life and what we know about it, and also for life on other planets. So it's not just me that's come up with this. This has been around for a long time. And I want to show you a little 28-second clip from the Star Trek Next Generation. If you're familiar with Star Trek, the original series, the science was really minimal, and the producers, I think, really underestimated their audience. But by the 1980s, when the Next Generation Star Trek came along, they were much more technical, much more science. So I thought this was an amusing one that works for this talk today.
Captain's log supplemental. The life form, which has significantly increased in size, is again attempting to communicate with us.
The universal translator is coming online, sir.
Ugly, giant bag of mostly water.
Bags of mostly water?
An accurate description of humans, sir. You are over 90% water surrounded by a flexible container.
So, despite Captain Kirk's consternation, data is correct in describing us as water organisms. And that little shiny creature, that was these crystalline silicon-based organisms who were shocked to discover these wet things. Anyway, we are bags of mostly water. So why is water important for life? I've just put a few summary slides. So you can look at that and you can see at the gross level, say the organ or tissue level, water is such an important part of our bodies, and not just us, but other animals and plants as well. Brain, 90% water. Blood, 83%. The only reason we can extract gases in and out of our lungs is because of a thin layer of water in the alveoli in our lungs. Even bone, you'd think it was a dry, inert substance. It's got 22% water. Bone is a living, growing tissue, and it has to have that water component. So that's at the gross organ level. You go down 2 steps, so organ, tissue, cell. Water is absolutely vital for how cells operate. All parts of the cell, growth, metabolism, reproduction, it's all depending on water. That's absolutely vital. So if you look a bit more closely at water molecules, why are they important? So water is composed of 2 hydrogens and an oxygen, and it's this property of having a large hydrogen or 2 small hydrogens and a large oxygen gives water a distinctive property. It's a polar molecule. So one end is more negative, that's the oxygen end, and one end is more positive. I always think of water molecule a bit like your hand. Here's the big oxygen and the 2 little hydrogens, and you've got negative here and positive here, and they're all going to start to link up. And it's this linking up that water molecules are sticky. So gives water a really high melting and boiling point, which is really good for life because now you have this wide temperature range where water stays as a usable liquid. If it's a solid, it's static, nothing moves. If it's a gas, like water vapor, it's too diffuse and disperse, not that useful. But the stickiness of water and the reason it bonds together is important. The other thing related to this polar nature of the water molecule is that they're really good for dissolving things. So the example I stole here from the web is dissolving sodium chloride, so table salt. The negative ion, like the chlorine, is attracted to the positive end of the hydrogen end of the water molecule, and the positive sodium is attracted to the positive sodium is attracted to the negative oxygen. This is why you put salt or sugar into water, give it a brief stir, and it dissolves so quickly. And it's not just these sort of ionic compounds, other things like organic compounds like ammonia or vinegar, they all dissolve really well in water. It's been described as a universal solvent. This is one of the properties that life really exploits for water. Like you think carbon compounds dissolving in water. So beyond this sort of atomic or chemical level, you can also think of water at the large scale. A lot of organisms use it for dispersing their seeds. So what you buy in the grocery store as a coconut, little hairy brown ball, is actually, in life, it's enclosed in a big spongy container that lets it float and drift across tropical seas to distribute itself. And because I like to keep tropical fish, I had to include this one. On coral reefs, a lot of the eggs are just dispersed into the water column. The larvae are on their own. They drift around in the current to distribute themselves around the oceans, or at least the tropical oceans. If you see a picture of coral reef, it's really crowded, full of packed. And it seems that there's a volume of larvae just waiting off the reef, waiting to come in to recolonize any vacant niches in that niche. Another important thing for water is its protection for life. So when the plant was getting started, there was no oxygen in the atmosphere. And there was water, and any living organisms would have been exposed to the extreme ultraviolet radiation from the sun. Today we've got oxygen in the atmosphere and an ozone layer, but in the distant past that didn't happen. But the nice thing about water is that it really blocks ultraviolet light. And you can see right here, ultraviolet light won't penetrate more than about 40, 50 meters in really clear water. So early organisms could evolve and thrive if the water was deep enough. The other thing about water is that most of our fossil record is based on water-related events. This is a picture of showing living stromatolites. They're a sort of geological biological construction. And they used to be really abundant in the earth until large grazing organisms appeared and started to devour them. But in few select places around the world, like Shark Bay in Western Australia, where the water is super salty, they can thrive. And they've persisted basically unchanged since the earliest years of the earth. Here's a local example from Waterton Lakes National Park in the southwest part of the province. These are just a measly 1.2, 1.5 billion years old, but the internal structure you can see. So you can see these layers and this dome structure. It's exactly what we see in the living forms. If it wasn't for water and these things living in the shallows and in the tidal zone, we would have no record of them. And we can come forward in time. The Ediacaran biota, originally found in Australia, now recognized worldwide. This bizarre collection of organisms, people still aren't sure what they are. Are they connected to modern life or not? Again, it was only because they were living in shallow water with sediments that they were able to be preserved. It's this ability, that stickiness, viscosity of water allows it to transport silts and muds and dump them on top of the remains of living things. And we can come a bit more local again, like Burgess Shale. Burgess Shale fauna was initially recognized here in Western Canada. It's now recognized worldwide in rocks of similar age. Again, we would have no idea of this if it wasn't for the properties of water. And coming to my favorite topic, all Alberta dinosaurs, their preservation depends on water and its mechanical properties. So I brought two things to attention here, the chemical nature of water and then its physical properties. And it made me think of this phrase, the medium is the message. Normally this phrase really annoys me. It's really vague and fluffy, and you can twist it around however you want. But here I thought it was relevant that water here is acting as serving two purposes here. So given the importance of water, you really want to know, where did it come from? How did we come to get it? We have to look at how the solar system formed. As far as we know, all life depends on water, and the only life we know is on our own planet. It's widely suspected that there's going to be life on other planets. And given the abundance of hydrogen and oxygen in the universe, it will probably be water-based. So, more than almost 200 years ago, almost 300 years ago, Immanuel Kant proposed an idea for how the solar system could have evolved or got started. So he imagined a cloud of gas and dust gathering around an early sun. And then somehow, magically, all these other details like a flat disk and planets and rotating and would somehow appear. But then 41 years later, French mathematician Pierre-Simon Laplace came up with a really nice physical model. He incorporated really sophisticated math for the time. And his model successfully predicts a flat disk surrounding a star that planets are rotating and orbiting. And it was a much more satisfactory model. And despite its age, 1796, it's still our preferred model today. And even better, with new space-based telescopes, we can actually see this happening now, it's a bit delayed. You got to think travel times for light from distant stars. But we can now see early stars with collections of gas and dust growing around them. And there's a really nice one. So those previous ones were from space-based telescopes. This is from ground-based system in Chile. They got this really nice image of spiral arms of dust and gas accumulating, and the star in the middle igniting. And there's an artist's impression of what this looks like. So once gravity compresses the star enough, it ignites. It's undergoing nuclear fusion, not fission, and it produces huge amounts of energy, clears out the inner part, and all this gas and dust is now going to start to accumulate into planets. So you go from that cloud of dust, there'll be random variations, some bits a little bit denser than others, and gravity will start to clump them together, and then you get a few larger objects which win the lottery to grow and accumulate mass, and it's sort of runaway effect of accretion of dust and gas onto a few starters. And they will clear out the areas around them to produce these larger planets or planetesimals. And so it's not just the random gas and dust, there's also a temperature distribution in that solar system. There's a temperature gradient in the solar system. So close to the sun, it's much hotter, and farther away, it cools off, which makes sense. And different types of materials have different melting and boiling points. And so rocks and metals will crystallize out, condense out at much higher temperatures than various ices and water-based compounds. And the result is that close to the sun, you will get metallic-y things and rocky things, and farther out, you get ices. And there's the dividing line. It's referred to as the frost line. So inside, it's hot and things vaporize. Outside, these things condense into solids. So the end result is that we have rocky, metal-rich planets, which are low in waters and ices, so like Mercury, Venus, Earth, and Mars. And then outside that frost line, we have the giant gassy planets like Jupiter and Saturn. And so I just wanted to zoom in a bit on this process of how you go from an amorphous, turbulent cloud of gas and dust to a nicely organized system of planets. So let's say stage one, the sun's condensed enough, gravity's pulled it together, it's ignited, but you've still got that cloud of gas and dust. Gravity will start to cause clumping to happen. And this snow line persists the whole time. So the sun is, she mentioned early on, the sun was only about 30% as bright as it is today, and it's been gradually getting brighter for the last 4.5 billion years. And it's actually going to keep getting brighter. In about 1 billion years, the surface of the Earth will probably be uninhabitable because it'll be too hot, but we don't have to worry about that today. So you've got these clumps starting to form. There's all sorts of interactions. And the rocky what started out as these planetesimals, maybe a few hundred kilometers in diameter, now we're starting to clump together. And there's this interesting intermediate zone here, right at the boundary. You've got dense rock, and low dense but giant gas planets. There's trouble here. These things are not coalescing the way the other parts do. And in the end, you end up with, instead of thousands and thousands of planetesimals, you've just got a handful of well-formed planets who have cleared out the areas around them. And that little troubled zone now is the asteroid belt. So it's planets, or protoplanets or planetesimals that couldn't get their act together because they're being tugged by the giant gas planets on the outside and the rocky planets on the inside. And this is important for how we accumulated our water later on. So I always liked this sort of diagram. I was always drawing it when I was a kid. And there's the rocky planets, quite small, on close to the sun, and the gas ones outside. Another component to think about is way beyond the icy gas planets, there's the comets. And where do they come from? The comets are described as dirty snowballs. They're mostly water ice, but they've got mineral grains and dust in them. It was long thought that comets were important for bringing water to the Earth, but that idea doesn't hold anymore. And this diagram is really misleading because it doesn't show you the proper scale. Here's the planets all drawn to scale, and it's measured out in what's called an astronomical unit. So 1 astronomical unit is the average distance between the Earth and the Sun. It's 150 million kilometers. And you can notice, look how tiny the rocky planets are compared to the gas giants. And also, this is a bit dated now, this diagram, because Pluto is not considered a planet anymore. It's actually smaller than the Moon. It's smaller in diameter and it's smaller in mass. And it's classed now as a dwarf planet. There's a whole bunch of things way out beyond Neptune that Pluto's related to, so it's not a planet. So I like this diagram because, again, it shows the relative scale of the size of the sun. Actually, when I see that picture, I can almost feel the heat of the sun on my face. It's really well done. You can even see the convecting cells on that sun's surface. Again, it highlights just how tiny the rocky planets are to the gas giants. Also, our moon is really unusual. It's really big compared to the host planet. When you look at the moons of the other planets, like Jupiter and Saturn, it's really peculiar, and that has a very interesting origin story, but I can't do that today. So here's Earth and Mars that we're going to focus on. They're not super close to the sun, but they're not super far away either. So in the search for life and other planets, exoplanet stuff, the astronomers talk about the Goldilocks zone. That's not too hot, not too cold. It's got just the right temperature conditions for liquid water on the surface of a planet. So we're definitely in the Goldilocks zone. And so the late stages of planet formation, most of the dust is being clumped together into rocky bodies, and you've got the few winners, what are now the protoplanets, are just mopping up the remaining stuff. And there's so much energy circulating around in this system that when some of these large objects hit the planet, they have so much kinetic energy that gets turned into heat, the planet completely remelts. And they talk about magma oceans that could be, so magma is molten rock at depth in the earth. Lava is molten rock at the surface, but for this they're calling it magma because there's just so much. The whole planet would completely remelt. And this was important for the evolution of the solid earth and eventually life on the earth, because every time the earth got melted, everything got reset. And it would take tens of millions of years for it to cool down again. I liked this image because you can imagine, so imagine you're standing on the moon somehow and surviving, and you're looking back at the earth. The moon and the earth, the moon is thought to have formed by a collision. So the early solar system was a very violent place. And the moon was the result of a collision between Earth and a protoplanet they're calling Theia. They got knocked stuff out into the orbit, and it coalesced and solidified into our moon. So imagine 4.6 billion, 4.5 billion years ago, you're standing on the moon looking at the Earth. The Earth is still this glowing hot ball of molten material, and there's perpetual rain of small bodies landing onto the Earth, building it up, but also keeping it very hot. It'd be pretty amazing. When the moon formed, it was much closer, and it was racing around the Earth at about 6 hours. An orbit would take 6 hours. You would get, tides every 6 hours, and there were tides hundreds of meters, kilometers high, racing around the Earth. Very different. But, as we know, things did cool down, and we have geologic evidence for liquid water on the surface of the Earth by about 4.2 billion years old, 4.2 billion years ago. This comes in the evidence of little mineral grains called zircons, which are they crystallize out at a very high temperature. And these early zircons that they're dated to 4.28 show evidence of having formed in the presence of liquid water. They have a very distinctive chemistry that says there must have been liquid water. And that means there must have been an atmosphere to keep the surface liquid and to insulate it. And life still has, we haven't got any evidence, direct evidence yet for early life at this time, but it's coming. And I thought this was a really nice picture. So we can look a bit more detail at water on the Earth. It looks like a wet planet, and some people say, well, maybe we shouldn't have called it Earth, which implies rocks and dirt. We've got so much water. But how much do we really have? I'm going to use some scientific notation I'll explain in a minute. So the total mass of the planet, so mass is a measure of how much matter there is. It's conventionally done in kilograms. So it's 5.97 times 10 to the 24, which means 5.97 followed by 24 zeros. It's a big number. So that's 10 to the 24. All the ocean mass is just 1,000th of that. You can see it's, so 24 is three orders of magnitude greater than 21. So the oceans represent just 1,000th of the Earth's mass. And let's write that out long ways. You can see why they use scientific notation. It's much more convenient. The other waters we have on the surface of the Earth, like ices, lakes, water vapor, they're at 1/10,000th of the total mass of the Earth. There's it written out long ways. And so when you put it in percentage terms, the oceans are just 2/100ths of a percentage. It's really tiny. So that picture on the right, it looks really abundant, but it's really not very much. And again, surface waters are even less. I found this picture. This is awesome. That big blue bubble, that's all the surface water of the Earth in comparison to the rest of the Earth. Makes you appreciate just how thin the oceans are. So the maximum ocean depth is about the Marianas Trench, 12 kilometers? Something like that? No, 8 kilometers, I think. No, I lie, it is 12. Mount Everest is something like 8 kilometers. The Marianas Trench is like 12. The average ocean depth is around 2 kilometers, but then you think that the Earth's radius is 6,370, give or take. So the layer of water represented by the oceans is just wafer thin. It's very, very limited. And yet so much happens in that thin layer. So where did our water come from? So earlier on I mentioned this existence of the asteroids. So here's the Earth, and then we've got this asteroid belt out here, just at that frost line. There's the frost line. The asteroids and their ices, that any ice they accumulated, sit just outside that frost line, so it's not sublimating. So just to be picky, when you go from a liquid to a gas, that's called evaporation. If you go from a solid to a gas, that's called sublimation. So but out beyond that frost line, it's so cold that even sublimation won't work. And so sure, these asteroids now have this ices and waters on them. How did they get it? So you have to come back to thinking about the solar wind. As the sun is doing its stuff, it's also ejecting mass. Thousands of kilograms, thousands of tons every second. And it's blowing out into the solar system. And don't think of it like wind, like gas wind that we have. It's just a flux of charged particles. It's mainly hydrogen. That hydrogen is streaming out away from the sun and bathing the planets and any asteroids. So if there's oxygen molecules sitting on the surface of an asteroid or a planet, and it meets this high energy hydrogen, it's going to react. And what do you get when you get hydrogen and oxygen? You get water. So there's your only equation in this talk. And Jupiter is the biggest planet, and it has a huge gravitational effect on the solar system. All sorts of features of our solar system are thought to be caused by gravitational effects of Jupiter. And one of the things it did was it nudged asteroids in towards the center of the solar system. And so you've got these ice-covered asteroids being directed towards the inner solar system. Some of them managed to get caught in the Earth's gravity field, and that's what's given us our water. And there's all sorts of geochemical evidence to say that this is the preferred source of our water, not the obvious thing you might thought of like the comets. So I want to say something now about why Earth and Mars are so different, and it really comes down to the size of the two planets. You can see that the Earth is twice the diameter of Mars, and this has two effects. The large size gives it a really strong gravity field to hold on to an atmosphere, and all that large size also allows the Earth to retain heat and give it a strong, warm, convecting core, and that's important for two reasons that I'll come back to later. So if we didn't have these two effects, a hot core and a large gravity, we wouldn't have the water that we have today. So let's look at Mars. It's small, it's dry, it's rusty, and it's cold. That rust is actually, Mars used to have quite a lot of oxygen in its atmosphere, but it's all reacted with iron minerals in the surface and turned it red. So the whole thing's a giant rusty thing. It does have some polar cap, some polar ice, but it's water and carbon dioxide. And if we look at the Earth, Earth too has polar ice, polar caps, but Earth's polar caps are just water. Thankfully, it's not cold enough for carbon dioxide. And Mars also has another southern polar cap as well. So the reason these two planets both have northern and southern polar ice caps because the sun's rays just graze the surface at such an oblique angle. It never gets very hot. And so we can compare again. Water can exist in three phases, a solid, a liquid, and a gas. Earth is unusual that we have all three phases present at the same time somewhere on the Earth. So we've got polar ice, we've got oceans and lakes, and we've got water vapor. So there's your solid phase, your liquid phase, and your gas phase. Mars has only one water phase, the solid, and it's either at the polar ice caps or it's frozen into the groundwater. We know about the subsurface ice from radar measurements, and there's been all sorts of probes gone to Mars, and they've mapped it and surveyed it in detail. I think it's the mass spectrometry. They can detect a strong signal of hydrogen in the Martian soils, which is only associated with the presence of water. There's lots of water ice on Mars. But there is, so I've mentioned usually Mars, their water is solid, but there is some melting visible, which is really amazing. So all these probes orbiting Mars and people scrutinizing thousands and thousands of photographs, they've seen these evidence of recent melting on Mars, which I think is really amazing. This Martian atmosphere is so thin and it's so cold, these events must be so brief. So this is ground ice melting and briefly flowing on the surface. And you can clearly see evidence for flowing water. And from, again, people studying these photographs and mapping Mars in detail, they've come up with these terrain pictures of what the surface is like. I think this looks a lot like the Red Deer River Valley. Steep sides, rapid erosion rushing down the sides, and you can see all the standard sedimentary structures like deltas and rivulets and rills and all sorts of stuff. And so these water flowing events must be so brief because it's so cold and so dry. But if you go back in time to Mars, like go back billions of years ago, there is clearly evidence that there was huge amounts of water flowing on Mars. So in this picture, the light is coming from the left, and the river are flowing from bottom to top. So we have this large delta, water radiating out. It's just like what we see today. And you can even see that in these impact craters formed from early in the solar system history, when there was still lots of debris flowing around, even after these impacts, the water was still flowing on Mars. And you can actually see there's a little river coming in here, and here's this little delta starting to fill in the pit. And again, after these had filled, you can just make out little tiny impacts from later on. So Mars was a very dynamic, active surface, but eventually the water stopped flowing because here's much later impacts. They have not been eroded and moved by any flowing water. And so the astronomy people, they can get approximate ages for the surfaces of the Moon or Mars by counting the density of craters. And so from the density of craters on this is a very ancient surface, billions of years old. But they've done calculations considering how much ground ice there is, how much is in the polar caps. There could be enough water on Mars today, if you melted it all, to give us an ocean around Mars several hundred meters deep. And Mars is peculiar that all that ocean would be on the northern half. The northern half of the planet is depressed, lower elevation. The southern half is all highlands. So I think it's because tectonics stalled on Mars that you just had this one very peculiar arrangement of continents and oceans. So given this amount of water and the fact that we have evidence for life developing within a few 100 million years on Earth, it's most likely that there was early life on Mars. I'd bet large sums of money that if we sent geology people and their hammers to Mars and they started beating on rocks, we would find evidence of early life. And in fact, I think we would get things like the stromatolites that I mentioned earlier, some of the earliest structured geologically macroscopic things that you could see. So this is an example from Australia. It's 3.4 billion years old. They're found in rocks of similar age all over the world. Here's our local example from Waterton Lakes. It's just a baby at 1.5 billion years old. And these things, these layering record daily, monthly, and annual tidal cycles. So it's really amazing the detail they record. It's thought that the organisms producing these were the ones that gave us our oxygen-rich atmosphere. So they're not algae the way modern algae is, they're actually cyanobacteria. They're a bacteria that can photosynthesize. And they were responsible for producing the oxygen in our atmospheres. And so there's the living examples today at low tide. So normally they're underwater, but here they are exposed at low tide in this Shark Bay locality. And I'm convinced we'd find something like stromatolites on Mars if we did. And again, it's because of the water preserving them. So now you come to the question, why is Mars so dry? Two reasons: weak gravity and no magnetic field. So let's look at the gravity problem. The Earth, as I mentioned, is really heavy, 10 to the 24 kilos. And it has a surface gravity of 9.81 meters per second squared. That's the average. It varies over the surface of the Earth. Mars is tiny. It's got 6.4 times 10 to the 23 kilos. Its surface gravity is 3.7. Mars weighs just 10% of the Earth, and its gravity field is just 1/3 of the Earth's. This weak Martian gravity can't hold onto an atmosphere or any water vapor. It will leak away into space given enough time. The Earth, we have a lot of iron. Our core represents 33% of the Earth's mass, and that's mostly iron. The average density of the Earth is 5.5 grams per cubic centimeter. If you think water is 1 gram, or 1 little gram of water is just 1 gram. 1 cubic centimeter of water is just 1 gram. It's this great mass that gives us a decent atmospheric pressure because there's enough gravity to pull the atmosphere down, and it pulls tightly enough that there's a decent pressure, and that pressure keeps liquid water on the surface so things can happen in oceans and lakes. It's important to have this gravity field because so much has to happen in there. You need a decent concentration of oxygen, or if you're an animal, or carbon dioxide if you're a plant, and it's keeping that high pressure is important for life on Earth, and that's due to our gravity. So I just want to stress that. Why do we have liquid water at the surface of the Earth? Because of gravity. And again, this strong gravity field also makes the hydrologic cycle important. If it wasn't for our strong gravity field, we wouldn't have a hydrologic cycle. The high pressure gives us liquid water at the surface, and it holds onto an atmosphere, and it makes water flow downhill, and it makes rain. This rain is important because the rain is going to fall on rock and minerals, dissolve them, transport nutrients down into the water so organisms can use them to grow. If we didn't have this hydrologic cycle, things would stagnate and stall. And gravity is also responsible for why hot air and water vapor rise. It's counterintuitive how it works, but you don't get convection or density-driven convection without gravity. So the wimpy gravity of Mars cannot do this. And Martian air pressure is just 1% of Earth. The air on Mars is extremely thin. You wouldn't last very long. I'm amazed that those little melting events I showed, I'm amazed that they can happen in just 1%, but they must be extremely brief. The other side of the story is our magnetic field. The Earth has a really strong magnetic field, and it acts like a shield. The magnetic field is driven inside the Earth, but its effects reach way out into space. And it's like a giant shield. I often thought of it, the old television cathode ray tube. You had a magnet and an electron gun, and the magnet can deflect and control the electrons to give you a picture on the screen. Similar physics is happening here. You've got those charged particles coming from the sun, the solar wind. They bump up against our Earth magnetic field and they're deflected around it. So that means we haven't got that solar wind impacting and literally impacting our atmosphere. The magnetic field is protecting us from that. And why do we have a strong magnetic field? It's because the Earth is so big. It's been able to hold its heat. So it's a general property of objects is the bigger they get, the ratio of surface area to volume gets smaller and smaller. So a big ball has less surface area to lose heat than a small ball. And so the Earth has been able to hold on to heat really well for 4.5 billion years. Little Mars was at a disadvantage. It had a high surface relative to its volume. It cooled down very quickly. Its liquid outer core became cold and viscous, couldn't convect, couldn't produce a magnetic field for very long, and it basically stalled. There is evidence in the rocks from satellites orbiting Mars. It did have a magnetic field in the past, but it's gone. And without that magnetic field, the Martian atmosphere was totally exposed to the sun's solar wind. So I found this is a nice picture, overly dramatic, but fun. You can imagine this flow of charged particles from the sun clobbering the Martian atmosphere and stripping it away. But our magnetic shield and our gravitational pull aren't enough to totally stop our loss of atmosphere. At the very top of the atmosphere, gas and water molecules are escaping. Right now, it's 3 kilograms per second is escaping from the Earth. You apply that over 4.5 billion years, things are going to start to diminish. So you have to ask, if we're still being affected slowly, why do we still have a dense atmosphere with water? Again, it comes back to this big hot planet that we're on. We have this heat engine inside the Earth, which is causing convection cells. So the same way a pot of water boils, it's hot on the bottom, cool on the top, you get hot material rising. This internal convection system in the Earth basically lets the Earth exhale water vapor. So it's constantly being replenished. So it's not just here visible on the surface, even from mid-ocean ridges, you've got water vapor and other gases being exhaled to replenish the atmosphere. So when you see these pictures of these erupting volcanoes, it's not just rock and ash and dust. There's also water vapor and noble gases like helium coming out from inside the Earth. So then the next question is, well, where does that water come from? Again, come back to the volume of the Earth. Our Earth's mantle is estimated to hold several oceans worth of water. The estimates I read, between 3 and 10 oceans are trapped inside the mantle. But it's not like Jules Verne's liquid water. It's water trapped in minerals, hydrogen atoms and oxygen atoms trapped inside all the minerals in the mantle. The mantle is such a huge volume. It's almost 3,000 kilometers thick. So there's this huge volume of water, and whenever that convecting mantle, when those iron minerals containing hydrogen get close to the Earth's surface, they start to melt, they release their water vapor. So that's why we have a continually replenished water supply at the surface. So one last thing I want to mention is, again, related to the unusual properties of water. Think about 1980s, there was the realization that at least once or twice in relatively recent Earth history, the entire Earth froze over. It's called the snowball Earth hypothesis. And it's certainly about 600 to 500 million years ago, we have really good geologic evidence that there was ice type sediments and evidence for glaciers and moving ice right down at what rocks that were at the equator. There's no doubt about it that it happened. And it was a huge surprise. And also, if you think about when complex multicellular life really got going, say the end of the Precambrian, beginning of the Cambrian, 600, 500 million years ago, some people have wondered if the sudden melting of snowball Earth was the start of a major event in Earth's evolution of life on Earth. So you can imagine this could be the Bahamas or Northern Australia, and it's fortuitous that the Earth was able to thaw, because water, again, an unusual property of water is that the solid phase, the ice, is lighter than the liquid phase. Most materials, when they solidify, you say you've got a liquid and you start to chill it and parts solidify, it sinks to the bottom. Water is unusual that the solid part floats. And if you remember the water structure, it's got the two hydrogens and the oxygen, and they link up. They form a very open, light structure. So it's really fortuitous that the ice floats, because with sea ice today, the sun can still shine through it. Algae and other microorganisms can still take advantage of the sun. And also, ice has a low thermal conductivity. So the ice actually helps insulate and keep a portion of the water liquid. If the ice was forming at the bottom, probably snowball Earth would have stayed frozen forever. You might get a little bit of melting at the surface, but otherwise we'd have been doomed, and we'd have been like the planet Hoth from the Star Wars galaxy. And I had to show, these things are awesome. I could watch these all day. I had to include that picture. It was so much work. That good old-fashioned stop-motion animation, none of this CGI stuff. So, to sum up, two planets, very different. They start off close together in the solar system, basically the same beginnings, but ended up very different. Mars, small, weak gravity, a cold core, no magnetic shield, an atmosphere with its water that leaked away into space, and no volcanoes to replenish lost atmosphere. And it's unusual, it's surprising that the largest known volcano in the solar system is on Mars, Olympus Mons, but it stalled billions of years ago. In contrast, Earth, we have a large mass, gives us a good, strong gravitational field, a large hot core, which produces a strong magnetic field, and then the atmosphere and water are able to be held tightly down and do their stuff. And because of that heat retention, we have volcanoes. Most of the volcanic eruptions on Earth happen out of sight under the oceans. But these volcanoes are important for replacing the lost water and other gases. And I'm done.